Let's look at the responses in the thermohaline circulation during some of the past events, like the last glacial maximum. This becomes critical, as we will see later on, also in potentially the carbon cycle response during glacial interglacials in terms of the 100 ppm or so change that is observed in the Antarctic ice cores. This is from a very nice paper in Nature based on data and model combination. So showing modern circulation, keep in mind that this is going from 1.5 kilometers to 4.5 kilometers. So it's intermediate to the bottom of the ocean, deeper ocean. The question is now, with global warming, how is the circulation responding and will continue to respond? We looked at the special nature of the Southern Ocean, its impact on Antarctic glacier variability and trend, and its exchanges with the rest of the world also matters. So we are looking at the polar front, the subantarctic front, and the subtropical front. So you can think of the cells, the Hadley cell, the Ferrel cell, and the polar cell, which is slightly modified in the Southern Ocean because of the channel configuration, but it's almost the same in terms of the jet stream and the fronts. Ocean is obviously very different because of the channel configuration. We already know that the Antarctic bottom water is formed at the edge of the ice shelves and so on, combination of very cold temperatures and brine rejection and other processes. That inundates the rest of the world. North Atlantic deep water is getting pretty deep in the Gin Seas, and then it's being pulled up at the polar front because of the Ekman divergence, and the Antarctic intermediate water and subantarctic mode water, the intermediate deep water, polar deep water, and so on, are kind of being pulled up here after being converted into surface waters over time. We are not saying how long these take, but you can see that they are going to come back and resupply the region where North Atlantic deep water is forming. So they happen over hundreds and thousands of years. The main thing we are interested in here is if there is a glaciation like the last glacial maximum, how does this circulation change or shift? Okay, several proposals have been made already by Robbie Togweiler and so on about the critical links between the pulling up of the North Atlantic deep water and these exchanges around here. Okay, so the proposed last glacial maximum circulation, so it is estimated and proposed, is that you still had Antarctic bottom water formation, but now you can see that the North Atlantic deep water, glacial North Atlantic intermediate water it became because of the ice extent pushing over the Gin Seas. The cold phytoplankton species that happen at the polar front were pushed way further down into the North Atlantic. So you'd have affected the meridional overturning and the deep water formation. So this is what it is saying here. And the surface water that is being supplied back is also coming as a different mix. So you have now IDW and PDW going here and supplying the Southern Ocean sites and becoming part of the Antarctic bottom water. Remember, these are to be validated with models because data probably will never be enough to completely configure these. That's part of the point of this podcast, that reconstructing paleoclimates continues to be very difficult just based on data, so we need to rely on models as well. So there are these other exchanges happening of the North Atlantic intermediate water mixing with the Antarctic intermediate water and subantarctic mode water. Mode water is something specific compared to deep water and intermediate water, which are created at the surface and they sink by convection. Mode waters are formed at a particular density and they follow isopycnals in a certain range. They are called mode waters. So there are differences in the processes of formation and their exit away from the surface or the region where they are formed. So mode waters need not necessarily be formed at the surface. There are processes that can create them and put them into the pipeline created by isopycnals, which are basically constant density layers. Remember that the ocean is well mixed near the surface, but it has stratification as you go below. There is seasonal thermocline, and then there is very weak stratification from a couple of kilometers down to the bottom. So flow tends to happen along constant density layers because that's energetically much more efficient. Okay, so these then should change the carbon cycle pathways as well. So where the carbon sinks, where it's going to come up, and so on is going to be affected. The paper says our results based on several independent indices show that AMOC changes, Atlantic meridional overturning changes, since the 1940s are best explained by multi-decadal variability. Basically this is saying there is no trend as such in the Atlantic meridional overturning. So anthropogenic forcing, which is appearing in ocean heat content, glacier melt, increased temperatures, water vapor, sea level, etc., is affecting the AMOC differently. Rather than an anthropogenically forced trend, the leading indicators in the subpolar North Atlantic today suggest that the current AMOC decline is ending. This is written more recently, just last year I think. We expect a prolonged AMOC minimum, probably lasting about 2 decades. This is assuming this natural multi-decadal variability continues, except as I said before in the context of El Nino, PDO and ANAO and so on. How the anthropogenic forcing itself modulates the natural variabilities at these time scales is not very well understood yet. So if prior patterns hold, the resulting low levels of oceanic heat uptake will manifest as a period of rapid global surface warming. So it's how the AMOC actually affects the heat budget at the surface. Okay, so this is now taking AMOC over separate periods, 76 to 98, 99 to 2015, and looking at slowdown of the AMOC and the associated SST patterns and the speed up of the AMOC and the pattern. So this is the multi-decadal variability we are talking about. So natural variability in this sense on low frequencies can add to global warming. So that's what this is saying about the resulting low levels of oceanic heat uptake will manifest as a period of rapid global surface warming. So if the ocean doesn't take up as much heat, it's going to show up as surface warming. Very simple. Okay, so between these periods there were also increased AMOC, again showing a warming pattern here, and a decreased AMOC showing a kind of a mixed pattern. So there are always multiple centers of action in this region, often referred to as the North Atlantic tripole. So you see here negative, positive, negative, and somewhat of negative, positive, negative. And this also shows up now in surface response. So how to switch time scales. Remember, thermohaline circulation is very slow, long time scale circulation when you take the global conveyor. And near the surface, on the other hand, you have changes in the Hadley cell and the polar front and so on. So this paper argues that the gyres themselves. So remember, these are the trade winds, westerlies, and then you have western boundary current and eastern boundary current. So you have a converging subtropical gyre in all oceans except the northern Indian Ocean, which is because of monsoon circulation doesn't have a distinct subtropical gyre, but the Southern Ocean does. The paper argues that, this is a summary of the paper, that these subtropical gyres are actually shifting poleward. That relates to how the Southern Ocean circulation would respond as well. Okay, the Thermohaline circulation we saw. And here you can see the difference between the North Pacific and the Southern Ocean gyre link to the polar front. It's very different because of this channel configuration of the Southern Ocean. So the point being that when we want to understand past responses to perturbations or past changes, we have to also use whatever we have in the modern periods to see what are the fundamental processes that are influencing these things. So that's what is going to determine the net response. Especially the Southern Ocean and the rest of the ocean responses are critical because of this idea of the heat uptake by the ocean. For example, in the tropical Pacific, if the global warming manifests itself as a La Nina-like pattern with colder or less warming in the east and more warming in the west, or it'll look El Nino-like with more warming in the east and less warming in the west, will determine how the trade wind system and ocean heat uptake will be affected. Remembering that ocean takes almost 93% of the excess energy, ocean heat uptake is very critical, and then we are saying the carbon cycle response to that is critical as well. So ocean response has the wind-driven component with this shift in the gyres and the polar fronts, and the thermohaline part, which is much slower. So complicated, but we have to do the best we can from past data and combining with models to try to understand these combination of timescales, patterns of responses, and impacts on global warming and feedbacks on global warming through carbon cycle. Interesting. This is an incredibly interesting problem. So it's a challenge, but it's a huge opportunity to learn the basics of our planet's ocean-atmosphere interactions at all timescales.